That's me, Mr. Emissions. You might also know me as CO2, excessive CO2. I've been hanging around since the beginning of the Industrial Revolution. I'm spewing from your cars, belching from your smokestacks. These days I'm everywhere, messing with the weather, mucking up the oceans, changing the climate. Pretty soon the whole planet will be mine.
Hey, not so fast, Smokey. We have a plan to put 6 existing technologies together to pull CO2 out of the atmosphere and put this guy back where he belongs.
Put me where?
Back into the earth, beneath the ocean floor. Here's how it's gonna work. We're gonna pull CO2 out of the atmosphere. We're then gonna take it and pump it down through the water column into the subsea floor, where in a short amount of time, it becomes rock.
That'll never work.
Oh, yes, it will. But we need your help. We know we have to cut emissions, but we now know that's not enough. We need negative emission technologies to put CO2 back where it belongs.
Wait. Let's work this out. Don't put me back. No!
Kids are demanding action. We can ensure that current and future generations move forward while we put CO2 back where it belongs.
Welcome to today's event, Solid Carbon, a Gigaton-scale climate solution. This event features an amazing panel of 8 experts working on different aspects of this project. I'm Tessa Owens, a graduate student at Columbia School of International and Public Affairs and the Earth Institute, and I'm excited to be one of your hosts for today's event, which is co-hosted by Ocean Networks Canada and the Virtual Blue Decade Initiative.
Hi, and I'm Tessa's co-host, Martin Sherwood, an Ocean Networks Canada senior staff scientist in the areas of gas hydrates, seabed dynamics, and carbon sequestration. We're happy to welcome everyone to this session, which is one of the many events happening at the Virtual Ocean Pavilion at the COP21 UN Climate Change Conference in Glasgow, UK. Our panelists today are joining the event from many different locations, but your co-host, Ocean Networks Canada, is headquartered on the traditional territories of the Lekwungen peoples. And we acknowledge and respect the Songhees, Esquimalt, and the Saanich peoples whose historical relationships with the land and the ocean continue to this day.
We also wish to acknowledge that today is Remembrance Day in Canada. Every year at the 11th hour of the 11th day of the 11th month, we gather in memorial parks, community halls, workplaces, schools, and homes to stand in honor of all who have fallen. The national ceremony has just concluded in Ottawa, but local ceremonies are occurring in different time zones across Canada and around the world. As we are about to begin this event, I invite everyone to, for a moment, reflect on the sacrifices of those who have gone before us.
Okay, thank you. And now we would like to introduce our panelists for today's event. So we're starting with Rachel Lauer, an assistant professor at the Department of Geoscience at the University of Calgary. Her research group focuses broadly on understanding the processes that govern the production and movement of fluids in the crust using numerical models of fluid flow and heat transport constrained by geophysical measurements. Then we have Karen Crawford, a professor of mechanical engineering at the University of Victoria. His research focuses on the design and system integration of renewable energy systems from wind energy generation to CCS, e-fuel production, and transport electrification. Then we have Ryan Foxall, a master's student with Karen in mechanical engineering at the University of Victoria, and his research focuses on the technical and economic implications of taking direct air capture, or DAC, to an offshore marine environment and integration with renewable energy.
We also have Heather Norton, who is a PhD student in mechanical engineering here at the University of Victoria. Her research focuses on renewably powered carbon removal systems coupled with ocean basalt storage. Heather earned a Bachelor of Science degree from Queen's University and a Master of Philosophy degree from the University of Cambridge. In addition to Heather, we have Terry Satterfield, who is a professor of culture, risk, and the environment with the University of British Columbia's Institute for Resources, Environment, and Sustainability. She and her colleagues and graduate students study how people perceive the social and environmental risks and benefits of new technologies and how to better assess the meaning people assign to environmental change. We also have Ben Tutelo, who is an associate professor in geoscience at the University of Calgary. In his research, he quantifies biogeochemical reactions using laboratory experiments, field measurements, and geochemical models. His group has been performing experiments and simulations to understand the rates of CO2 mineralization in sub-seafloor basalts. Romany Webb is our last panelist and is an associate research scholar at Columbia Law School and a senior fellow at the Sabin Center for Climate Change Law. Romany's research explores legal issues associated with the development and deployment of negative emissions technologies on land and in the oceans.
Now I would like to ask all of you in the audience to also introduce yourselves to us a little bit. And we'd love to hear from you where you're joining us from today. And on your computer or phone, please visit www.menti.com and enter the code 2265-8743 and let us know where in the world you are now. Okay, we have New York City, Langford, here right next to Victoria, Calgary, where lots of panelists are today. We have the Esquimalt First Nations. We have Canada in general. Very North American centric here.
Hopefully we'll have more audience members join us from elsewhere in the world as we go on. And it's great to see where everyone is coming from. We have a truly international crowd, a couple people coming in from Arizona and Tempe. So later in this event, as an audience member, you will have more opportunities to participate by answering questions and sharing your reactions in the chat. So keep in hand this Menti code because you'll need it a few times later. With that, let's begin the main event. I would like to first invite Rachel to the stage to give us a general intro to the Solid Carbon project. What is the big idea with this project, Rachel, and where is your team hoping to do it? What is driving the need for this type of project, and how is it different from other initiatives?
All right, well, good morning, and it is great to see people from so many places in attendance here. Just requesting control. Okay, so before I introduce the Solid Carbon project itself, I wanted to first highlight the need for scalable technology like solid carbon that really does have a chance of combating climate change. The Earth naturally cycles carbon between the solid Earth and the atmosphere through a number of processes, such as volcanic activity, which is really the main contributor to the natural carbon flux to the atmosphere. With only a small fraction of the carbon in the Earth system lying in the atmosphere, this is the carbon we're seeking to remove because this is where it has the potential to impact the climate on shorter timescales in terms of decades due to its warming potential as a powerful greenhouse gas. Do I have control? Okay, if somebody could advance the slide, I'm having an issue. Oh, got it. All right. So since the beginning of the industrial age, we have altered the climate by removing buried carbon from the ground and using it as fuel that then impacts the global carbon cycle. To put some numbers on our impact today, each year humans are emitting 51 gigatons of CO2 as compared to the annual supply from these natural sources, which contribute about 300 megatons to the ocean and atmosphere. This means we are producing 170 times more carbon than the Earth. Thank you. It's now well recognized that climate scenarios for the Earth to stay within the limits set by the Paris Agreement must include net technology or negative emissions technologies to actually draw down excessive CO2 from the atmosphere on a scale that will have an impact and allow us to maintain below 2 degrees or below 1.5 degrees Celsius warming. Looking at this graph shown on the left, there are different regions. The green regions are sort of the conventional abatement technologies, renewable energies, nuclear, et cetera. The brown regions represents advances or innovations in technology that allow us to electrify our vehicles. And the blue area is where solid carbon sits in terms of negative emissions. And these are the ones that actually are removing carbon from that carbon cycle and permanently sequestering it and keeping it out of the atmosphere. So the big idea for solid carbon, sorry, advanced slide again. So solid carbon is building on 100 years of CO2 capture technology from countries around the world. We are adopting the sequestration technology of our predecessors and building on it by adding renewable energy and direct air capture to actually create a negative emission technology framework that has the potential to globally scale. The vision is to extract CO2 from the atmosphere using direct air capture technology, which we'll hear about later. Then using ocean-based wind and solar energy, take that CO2 and inject it into the subsea floor basalt, where it will mineralize and remain permanently as rock. So how does this happen? CO2 that's injected into this cool volcanic rock under the ocean reacts chemically with them to form solid minerals like calcium carbonate, also known as limestone, which is mimicking these natural processes of rock weathering. These subsea rocks have the potential to provide vast capacity for hundreds of years of emissions. And they also have natural physical safeguards that protect the oceans and humans and can be located at safe distances from potential interference with ongoing human activities and natural ecosystems. Next slide, please. So the question is, I guess, why Cascadia? Most of the Earth's crust below the oceans is composite. So there is massive and widespread sequestration potential, which is shown on the right-hand side here. But we're focused on the left here on the Juan de Fuca plate, also known as Cascadia, where about twice the size of Vancouver Island may have the potential to provide safe storage for decades worth of global carbon emissions. For the demonstration phase, we want to focus on a well-studied area that has existing infrastructure that can aid in the deployment of this technology. In this area, there are multiple existing scientific boreholes that penetrate the crust, can be used in the injection phase, and a monitoring network established by Oceans Network Canada that can aid in the monitoring of the carbonation post-injection. Also, the reason these boreholes exist is to study the hydrogeology of this system so we know how fluids move in the ocean crust and that the crust is permeable or allows fluids to move easily from one place to another. Together, these conditions make Cascadia the ideal target location for demonstrating the technology as soon as 2025.
All right, well, thanks very much, Rachel, for that great overview. Now I wonder if we could get some more in-depth understanding of carbon capture from Karin. And while Karin is speaking, let's ask another poll question. Again, use the second tab or phone and visit menti.com and enter the code 22658743. We have a little question for our YouTube audience coming up. How many tons of CO2 could potentially be sequestered in subsea basalts? And while our audience is submitting answers to this question, Karen, Heather, and Ryan, please give us a sense of technologies out there and whether they could be used for subsea floor sequestration. What are the challenges with this approach, and why are you thinking capturing at sea rather than on land?
Great, thanks, Martin. See if I can get to the next slide here. Yeah, perfect. So this is back to the overview of the kind of engineered system we're looking at. So our part of the project of solid carbon is to look at all the different options that are possible for capturing and delivering CO2 to have that injection happen under the seafloor. So we're looking from everything, including industrial point capture, things like cement plants on shore, direct air capture, which Ryan's going to talk about in a bit more detail, onshore as well. And then we're looking at pipeline and or ship transport options to get that out to the injection site. And then what we're really trying to do and what's required to have this really net zero carbon system is to power renewably. So we're looking in particular at utilizing offshore wind energy, either the fixed bottom offshore or the floating offshore wind technologies that are emerging. And so we're looking across different water depths and what the cost curves look like there and sizing. And then we're looking at even potentially integrating direct air capture offshore with that offshore wind energy generation. To power that transport and also buffer the operation of our system, we're also looking associated at hydrogen production, potentially ammonia production to fuel, say, ship transport back and forth there. And then we're also exploring some additional options on the far right there, this idea of using more mobile platforms to do the capture of both wind energy as well as the carbon capture. So ultimately, again, being able to capture and then deliver the CO2 for injection. So that I'll turn it over to Ryan to give an overview of the various CO2 capturing technologies we're considering.
Thanks, Karen. If we could just swap to the next slide there. So where can we actually pull our CO2 from? Well, we basically have two options: from the atmosphere, from the air, or from the seawater. So we have direct air capture and we have seawater capture. Next slide, please. So looking first at seawater capture, why would we capture from seawater to begin with? Well, for one, it has a higher CO2 percentage by volume. So there's more opportunity there. It takes advantage of electrochemistry. So there is more efficiency you can get out of that. And basically what happens is you're shifting the pH in the ocean water to be more acidic, which will drive the CO2 off of the ocean water. One thing that it requires a huge amount of water to be pumped for this. And so it has a huge energy requirement there. And currently it's only being done at a lab scale. So it's not something we're pursuing very actively right now, but we will be pursuing it in the future. Next slide, please. So basically looking into direct air capture, how does this work? If you could hit next, please. Basically, we have the capture and the regeneration component. So CO2 first comes in contact with a sorbent, and that's going to be either a solid sorbent or a liquid sorbent. And then to actually drive that CO2 off of the sorbent, we can use a variety of different methods, but the most common is a thermal or a pressure swing. So you can see we basically come up with four different options there: solid sorbent or liquid solvent, and then thermal pressure or electrochemical regeneration. Next slide, please. So just looking through some of the pros and cons of the different approaches. If we go first into the solid sorbent, these are much smaller designs. They have a low grade heat and they have a short cycle time. So they basically go back and forth from capturing to regeneration, and they cycle back and forth. Some of the cons of this technology is that the capital costs are dominated by the sorbent itself. It's a new industry, so it involves scaling up an entirely new industry, and the sorbent performance, there's a fair bit of uncertainty in how it'll actually perform once you take this offshore. And then we look into the liquid solvents with the thermal regeneration. These plants are built to be huge. They're built to be on the order of 1 megaton a year. So they can take advantage of economies of scale. They have a continuous kind of 2 cycles, working in tandem, and it's a continuous operation. So you end up with a continuous output of CO2. And this works off of an inexpensive solvent and an existing industry experience. Some of the cons with this, though, is that it does require some replenishment of both your solvent and your water. It requires a high degree of heat. So, on the order of 900 degrees, which if you're doing this offshore, we're limited in our options to what we can actually do there. And because of this high heat, the ramping is also limited. We can't turn it on and off as quickly as we could with the solid sorbent system. So next slide, please. And just kind of taking a look at what's going on in the industry, we basically have 29 companies or so working in the space right now. You can see the liquid and solids, which we just discussed there, is kind of the most prominent, with about 10 in the solids and 2 in the liquids. And then we have everything from electroswing, mineralization, more electrochemistry, and then some sort of cryogenic captures. So there is a fair bit of attention in kind of the electrochemical side of things, as well as the solid and liquid with thermal generation. Next slide, please. So what does it mean to actually take direct air capture offshore? Well, for one, you can see that it's quite a harsh environment, obviously. So it needs to be susceptible. It needs to have resistance to motion, corrosion. The sorbent itself will need some adaptation in order to deal with both increased water presence and salt spray in the air, which will require some additional equipment, such as more robust fans or demister pads to actually remove those salt particles from the air. Then we're put up against size, space constraints. Obviously, you can see these platforms are limited in how much deck space we have, as well as how much weight they can actually take on. And then that builds into kind of the system level implications, such as the need for energy storage and for different operation altogether. So I'll flip to Heather now, who will fill us in on the offshore wind.
Thanks, Ryan. So unlike direct air capture, offshore wind has been operating offshore since 1991. And in that time, it's had a good opportunity for the cost to go down and the technology to mature. So turbines today are much larger, their blades are wider and they're higher, which allows them to generate much more power, which is what's driven cost way down. At the same time, platforms have matured to allow wind to float, which means that deeper water can be targeted for wind farms, greatly expanding the available area where we can put this technology. Similarly, the offshore industry has given us a variety of technologies that we can use to progress this concept. So we already have platforms, drill ships, ways of doing maintenance that can operate in deep water and extreme conditions. We also have pipelines, pumps, heaters, and compressors that are designed to be safe and efficient for carbon dioxide. What we've never tried is the ability to inject carbon dioxide and store it in ocean basalt offshore. So although there are things we can learn from the onshore technology, there are still some pieces that we would need to put together. The benefit of this, once we have all these pieces and we can put them together, is that we can create a system with some really interesting properties. Specifically, we could move far enough offshore not to compete with the grid. And this is very important because we need renewable energy to onshore to be part of the decarbonization efforts that we were talking to you about earlier. And it's not clear that we can develop fast enough to do everything that we would like to do with that energy. So, but if we move offshore, what we need to do is address the fact that the wind energy that we're getting is not steady. And so we will create a microgrid where we use a combination of wind power with energy storage or potentially fuel synthesis, so that we can make sure that we're getting the best bang for our buck from the energy that we have, while also having reasonably good utilization of all of the technology that we've invested in. And there are a variety of configurations that we can use to do that. The one approach would be to sort of scale up and use a centralized mothership. Another would be to distribute into smaller technologies that we can deploy modularly. And in the first case, you get benefits of economies of scale. In the second case, you learn faster as you roll out more and more of the same technology. But in any case, the prize is the same. What we want to do is take advantage of the massive global opportunities to scale up a technology of this kind. Here is a map. Wind resources with wind speed greater than 8 meters per second and in water depth less than 1,000 meters are highlighted in blue. We've taken the available ocean basalt capacity and we've looked for specific traits that we think make it more viable, like having a thick cap rock, being in an exclusive economic zone, etc. And it's color coded based on how close it is to the wind resource. And what you can see is that we have lots of areas towards the poles where we have countries that would have potential to deploy this at large scale. So they include countries like the US and Canada, Greenland, Norway, potentially South Africa, Australia, New Zealand. And the overall capacity is much, much greater than what we need for negative emission technologies.
All right. Well, thanks very much. And wow, all this engineering stuff sounds really complicated, but somewhat doable. So that's great news. Now, let's take a look at the audience's answers to our question on menti.com. And you were asked to estimate how much do you think the offshore ocean basalts can actually hold. So we have someone not quite so optimistic at 250 gigatons. And then it's almost a half-half between 10 times or 100 times that much. And the answer is actually the maximum there, 250,000 gigatons. So that's actually quite a large amount of estimated host capacity for the offshore basalts, meaning that from a practical point of view is really unlimited. So great of those of you who've done and guessed the very big, the largest number, which is good. And yeah, more room for optimism.
All right, this has been super interesting. Martin and Curran, Ryan and Heather, thank you so much for that overview. Now that we've learned about the capture part of the solid carbon project, I guess we really need to start wrapping our heads around what happens to the CO2 once it's beneath the seafloor. So I'll turn to Ben and Martin for explanations about this next segment of things. And while Ben and Martin are speaking, we're going to pose a third question to our audience. So again, you can visit menti.com and enter the code 22658743. Try to guess how long it would take for a megaton of CO2 to mineralize inside subsea floor basalts. So while our audience is submitting answers to this question, we're going to turn to Ben, who is going to explain to us in simple terms what happens when CO2 is injected into subsea basalts.
Can people hear me out there? Yes, I cannot tell.
You sound great, Ben.
All right, thank you very much. So I want to talk about durable CO2 storage and what happens with the geochemistry of this technology. So as we've just heard from Curran and his team at the University of Victoria, one of the big steps in this process is capturing carbon dioxide directly from the atmosphere or from ocean water if that technology becomes feasible. But after that, we need to pump CO2 below the seafloor, and ultimately that CO2 needs to turn into rock over some time scale so that it is immobilized and ultimately prevented from warming our atmosphere. So how does basalt carbonation happen? And that's the question that Tessa asked me. And so I'm happy to try and answer that for you today. So this picture in the background here is a nice vesicular basalt. It's got lots of big bubbles in it. So those are ultimately, whenever this basalt was erupted, it had big gas bubbles in it. But what we're trying to do now is inject CO2, represented here by these smaller bubbles here, into the basaltic aquifer, allow it to react with the rock, and then turn into a solid carbonate mineral, such as this mineral calcite here on the right-hand side. So we have this step 0, injection of CO2, step 1, dissolution of CO2, step 2, basalt dissolution, and finally, step 3, carbonate dissolution. And so for those of you out there that have ever used a soda stream, you know very well step 0 and 1, right? So we inject CO2 into our bottle in our soda stream, and then some of that CO2 dissolves. So CO2 actually dissolves quite quickly. As we know, again, from our soda stream, we aren't waiting hours every single time that we inject CO2 into our soda stream bottle. In fact, it should dissolve almost instantaneously, except the problem is that CO2 is only so soluble in water. So once the CO2 is injected into an aquifer, in this case on the left-hand side, that CO2 dissolves into the water near the CO2 plume that is formed in the subsurface, but ultimately you need to bring in new water in order to dissolve more CO2. And so this reaction, although this chemical reaction is very fast, as we all know, ultimately some of the CO2 remains in the supercritical phase in this case, or the gaseous phase as we would think of in our soda stream example. If that's the case, then we have to think about how water is going to flow around our CO2 plume in the subsurface. And so this is just a plot of liquid velocities. So where we have water moving about 5 meters per year in much of our aquifer, but it moves very slowly in that CO2 plume itself, ultimately because that CO2 plume makes the basaltic aquifer much less permeable to water than it would be otherwise. And so that's one of the big challenges for dissolving all of the CO2 that we plan to inject into the aquifer, is how quickly it can dissolve. So again, moving past that, so injection of CO2 into the subsurface, now we're thinking about what's actually happening to the water itself. So supercritical CO2 plume in the subsurface, so supercritical being that sort of liquid separate phase CO2 that would exist in our aquifer, will increase the partial pressure of CO2 and ultimately decrease the pH. And so if we see here, we're thinking pH of seawater is about 8, no matter where you're at in the world. When we inject this large slug of CO2 into that aquifer, we're going to have pHs much lower than that, probably between 4.5 and 5. So solid carbon, our technology, we have a high partial pressure of CO2 represented here by this variable FCO2 on the x-axis, but the fluid pH is going to be low, but not that low in our aquifer. And so what does that mean for step 2, basalt dissolution? Basalt dissolves faster at low pH. We know this from laboratory experiments dissolving basalt in well-controlled reaction vessels, but we know that carbonic acid is a pretty lousy acid actually, and it cannot make the pH very low. So here's neutral pH. We're all sort of familiar with that pH of 7 being neutral pH in most Earth systems and our water that we get from our tap water. Seawater pH is naturally around 8 or so. And so if that's the case, we would expect that when we inject CO2 into the aquifer, that this high partial pressure of CO2 is going to lower the pH to around 4.5. But if we compare the reaction rates between this higher pH at seawater levels and the lower pH at this high partial pressure of CO2 levels, then we end up actually having more or less equivalent reaction rates in all of those aquifers. So between here and here, the reaction rate's about the same. So this CO2 is not actually making the basalt dissolve much faster than it would if it were just in a normal seawater aquifer. But here's where the big issue occurs. Whenever we lower the pH down to 4.5, the solubility of carbonate minerals increases very, very rapidly with decreasing pH. So pH doesn't really affect the basalt dissolution rates, but what it does affect is the solubility, so the amount of the mineral that you need in solution before you can actually precipitate it and make a mineral or turn your injected CO2 into a mineral like calcite. And what we see here is that as that pH drops down towards 4.5, that solubility of calcium carbonate in this case increases very dramatically. And this is something that should be very intuitive to those of us who have ever tried to get scale outside or out of the inside of our hot water heaters or outside of the inside of our kettle, we use a weak acid in order to do that, in order to dissolve that calcium carbonate scale. So since pH, again, doesn't really affect the dissolution rates, the main constraint is the solubility of calcium carbonate minerals or carbonate minerals like calcite. So if we just look at this on face value, if we want to make more carbonate out of our CO2 that we inject, we just need to inject less CO2. Grimace emoji, right? Because I don't want to be the one that tells our grandkids that we actually have to inject less CO2 in order to stay below our climate targets, right? So ultimately, we need to think about how can we get past this issue of needing to inject less CO2 and still make that CO2 into solid carbonate minerals. And so what we've done is done some simulations looking at normal seawater, right? Not trying to manipulate the seawater at all and having this large partial pressure of CO2. And these are conditions that are representative of the Cascadia Basin off the western coast of British Columbia in Canada. So what we see is that ultimately the minerals of basalt, olivine, pyroxene, and plagioclase are converted to carbonate minerals like dolomite and anchorite, even though that pH is quite low in this system. So we can still expect significant mineralization even at the gigaton per year scale. So what are we going to do now? So my colleague Martin is going to talk about monitoring and potential risks right after us. But what are we doing as geochemists to try and understand these processes right now in our laboratory? So we have Dr. Juan Carlos Diabeso working on dissolution rates of plagioclase, one of those minerals of basalt, to try and understand not just how much carbonate we can possibly make, but how fast it's going to be made. And he's using specialized laboratory reactors in order to do that. And also we have Juan Carlos working with Dr. Adedapo Awolayo in our lab, trying to understand, okay, if we know the dissolution rates of plagioclase, how rapidly can we expect those minerals to convert into carbonate minerals? And what we do with all of that data is then run simulations actually looking at the dissolution rate of the CO2 into the aquifer fluids, looking at the dissolution rate of the basaltic minerals, and then finally looking at the carbonation rates. And here is one of those simulations. So I could just loop this here. And we're injecting, in this case, 0.5 megaton per year for 10 years, where now this time in the upper left corner is time in years. And so you see this CO2 plume exist. It turns gray there. It's that large bubble, essentially, of CO2 surrounding our injection well. And ultimately, that CO2 dissolves over thousands of years and mineralizes.
Wow. Thank you so much for that explanation, Ben. That was really interesting. One of the questions that I have about all of this, I think is directed towards Martin. I'm wondering how safe this is and whether there's potential for CO2 to somehow leak back up into the ocean or into the atmosphere.
All right, thanks, Tessa. And yes, there's absolutely a need for monitoring this and basically prove that it is safe. I'm running in the wrong direction here with the presentation. Apologies for that. So one of the big advantages to start with the Cascadia Basin is that we already have a monitoring observatory in place. And the two things we would really like to do here is to ensure safety and also to track what's happening to the carbon underground. Ben and his team did a great job or still doing a great job in modeling and basically showing what is likely to happen, but we definitely also want to make sure that we track that. So in terms of safety, just wanted to reiterate that we have 3 safety mechanisms already in place. So it's a relatively safe thing in our minds to do in the deep ocean. First of all, we are injecting into the deep ocean basalts, which are underneath a layer of sediment rock. And if you look at the porosity of the sediments compared to the basalt, actually the sediments are really, really dense and compact. And what we know from the existing fluid flow experiments that already happened is that the sediments actually act like a capped rock on top of the basalt rock. So all the fluid movements already trapped underneath the sediment. But if that is not enough, and for some reason we do get a leakage out onto the ocean floor, this is a maybe somewhat complicated diagram showing that the CO2 at that depth is actually denser than water. So what you can see here is a pressure versus temperature plot of CO2 density, and then you subtract water density from it. And CO2 typically, as Ben explained, in your soda stream, you have bubbles and some of it dissolves, but usually the bubbles come up. Whereas at certain depths, at relatively low temperatures, the CO2 is actually more dense than water, and it would just stay on the seafloor. And so we don't really have to worry about it then migrating all the way back into the atmosphere, where we try to extract it from and put underground. So that's already a very good second safety measurement or mechanism in place. And the third one is even more complicated, is that while the CO2 might be migrating through the sediments, it actually has a potential to form a so-called CO2 hydrate. And that is a relatively stable form of CO2 and water molecules to form like a thin sheet of ice. And this complicated plot here has, again, temperature versus depth, and depth is equivalent to pressure. And if we just focus on this gray-brown line here, this is what the temperature in the ocean looks like. So it's relatively warm at the surface and then gets colder when we go into the ocean abyss. And here, right when we hit the seafloor, it's just a couple of degrees centigrade. But then when we enter the sediment, it becomes quite warm again. So if it's a thin sedimentary layer, it's going to warm really quickly. Or if it's a relatively thick sediment layer, with the second line here being the top of the basement rock below, it's also increasing in temperature, but not quite as quick. And the only other line of interest here I'd like to point out is, where would CO2 hydrate be stable? And we know that in the upper parts of the ocean or in the air, it's not stable. So this would immediately dissolve again, and we would lose the CO2 trap. But if we go into the ocean water, it's actually, it's stable under these conditions, which are above what the current conditions would be at that depth. So that means as long as the green is above this gray-brown line, it's actually stable. But in the ocean, it will dissolve because the water takes away that CO2 and dissolves that structure. But once we hit the sediments, the water might get oversaturated with CO2, and then we would form this hydrate ice layer, which then acts as a potential trap. So if we have any leakage, it might not even reach the seafloor. It will trap itself by forming a hydrate, but that only happens at the really shallow parts here in the sediments. So that's an additional safety measurement. So we probably don't have to worry about gas leakage. But still, something else talking about safety here is, what if we put too much pressure while we're doing the injection? And so this is work that's done by Ine Johnson, our solid carbon postdoc here at Ocean Networks Canada, who is doing some modeling. And at the moment, she's setting up a very broad model of potentially even several injection sites and then having faults in the subsurface, that if we put too much pressure on these faults and there's a geological force field in place, that these faults might actually rupture. So how much does it take for these faults to rupture? How much seismicity do we induce during the injection? And if we have just a random suite of faults and sort of relatively high pressure, we can see likelihoods. So the redder here the fault, or the warmer the color of a fault, the more likely it is to rupture. And these are just really high and sort of random distributions of faults, really high pressures. And there are actually some faults that might be triggered. And here's just the suite of some faults might take a lot of pressure to actually trigger and make a little small earthquake, and some don't really take that much. But when we look at the tectonic stresses and the fault orientations, Ine rather, found that if we have the faults aligned in a certain way, and we know in the Cascadia Basin, they're actually more or less north-south, so not this randomly distribution, but more like a north-south orientation, and we have the maximum sort of stress field perpendicular to it, so which is like this, except you would need to, if we're doing the real model which is coming up next, we would need to flip this to 90 degrees. We actually have a very, very small likelihood of triggering these faults. This is the kind of situation, whereas if the stress field would be different in the Cascadia Basin, which we know it isn't, then there might be a higher chance of triggering these faults. So we think even there that it's a relatively safe thing to do. And in terms of ensuring that we know what's going on, as mentioned before, many times we have this Ocean Networks Canada Neptune Observatory here where we have nodes and we can plug in instrument platforms with all the suite of instruments that we need to monitor what's happening on the seafloor in the subsurface. So we want to include a sonar that can see if there is any leakage of bubbles, which we don't expect, but we want to prove that there isn't. We also can have a camera that actually looks at the injection well and see that there's no bubbles coming out at the side and sort of leaking into the ocean, where we know they're very dense, so they would stay on the ocean floor. And we can put temperature sensors, but also seismometers or distributed acoustic sensing, very new technology, strings on the cable that measure really tiny tremors from the injection process. And we would know what's going on in the subsurface. There are also other methods like electromagnetic methods where we can differentiate between the CO2 gas versus a liquid. So gas don't really penetrate the electrical signals very well, but fluids do. So we might see a change when the gas eventually turns into a dissolved CO2 medium, and then it could mineralize over time. So we want to have as many of these possibilities there as possible. And just to back us up, to have complete control of what's going on, we also want to do active fluid sampling. So there are already these existing boreholes. If need be, we could drill more. That's a very well working technology. And then insert these fluid capture units, which are basically osmotic samplers that suck in fluids constantly. And then if we do add tracers to our injection fluid, then we could actually see that we already track something arriving that will come and arrive at the monitoring borehole at a certain time. So we know how fast things are flowing during the injection. And we have the option to use different kinds of tracers, some so-called conservative tracers that go just along with the flow as background, and also the so-called reactive tracers that basically mimic this, what happens to the CO2. So if we get these conservative tracers arriving at the monitoring borehole, but none of the reactive tracers, we know that the CO2 would stay behind or is staying behind. And we can take these samples on a regular basis and take these fluids back into the lab and analyze them. Okay, that was a very short excursion on all the monitoring options we have. And before we get to the regulatory and acceptance license, back to Tessa.
Yeah, thank you so much for this explanation, Martin. It's very interesting to learn about CO2 hydrates, methods of monitoring them, and modeling possible induced seismicity. So let's circle back to our audience's answers to our question that we posed earlier about how long it would take for a megaton of CO2 to mineralize inside these subsea floor basalts. We've pulled both Ben and Martin up to talk about the answers here.
Yeah, wow, there's a great range of answers. I think it's interesting that nobody said thousands of years. Lots of folks said tens of years. Well, half the folks said tens of years. Many said hundreds, or many said tens of thousands of years. I think some of the CO2 will certainly be mineralized over the 10-year timescale, but it is unlikely that all of that megaton that we would inject would be totally mineralized over tens of years. Perhaps a significant proportion of it would be completely mineralized over the hundreds of years timescale. But I think if I were a betting man, and I'm betting based on my own current simulations of this process, I would say in the thousands of years is what I would expect for that megaton to dissolve. But perhaps it could even take tens of thousands of years if things were to go very slowly.
Yeah, for that, it's actually great to know that we do have so many seals and safety mechanisms in place if it really takes that long. But as Ben, you didn't give us a very definitive answer because it seems like we don't actually know for sure. So this is basically telling us that even if it does get to really, really long times, I think we are still safe.
Agreed.
All right. Thanks. All right, so.
Yeah, thanks, Ben and Martin, for leading us through this segment on CO2 storage. We've touched on safety and monitoring, and this raises questions about how society may react to this kind of project. There are questions about the legal framework as well as social acceptance. So we'll turn to Romani and Terry now for explanations about these important topics.
And while you're speaking, Terry and Romani, we're going to ask a couple more questions to our audience. Again, visit menti.com and enter the code 22658743. And we want to know from your from our YouTube audience, how much of you agree with the following statements. Even if we stop emissions of CO2, CO2 sequestration will be needed in the future. So do you agree with that, or do you not agree with that? And then the second question is, this project is worth pursuing further. Do you think we should continue, or do you think this is a crazy and silly idea? All right. And while our audience is submitting answers to these questions, Roman and Terry, please explain these aspects of regulatory and social considerations for this kind of project.
Thanks, Martin, and thanks, Tessa. As we've heard, the solid carbon project is really quite a novel project, and so it raises some novel legal, regulatory, and other social science questions, which we're addressing as part of the research project. I'm going to start off talking a little bit about the legal questions, and then I'll hand over to Terry to talk about the social acceptance piece. On the legal side, because the solid carbon project would happen offshore in the oceans, both international and domestic law are potentially relevant. Under international law, generally speaking, coastal countries have jurisdiction or authority over ocean areas within 200 nautical miles of the coast. The target site for the solid carbon project, the Cascadia Basin, actually extends through areas under the authority or jurisdiction of both the United States and Canada. And so depending on exactly where different project-related activities take place, they could be subject to the domestic laws of one or either of those countries. Both countries' domestic laws are informed to various extents by international law. Lost my slides. At the international level, in the climate change space, the key agreements are, of course, the United Nations Framework Convention on Climate Change and the Paris Agreement. Neither of those agreements include provisions specifically regulating carbon capture and storage, but they both do appear to implicitly approve of it. So both agreements talk about the need to protect and enhance greenhouse gas sinks. And the term sink is defined really very broadly to include any process or activity that removes a greenhouse gas from the atmosphere, which is, of course, exactly what the solid carbon system is intended to do. But as I said, the Framework Convention on Climate Change and the Paris Agreement don't establish any sort of regulatory or governance framework for those sorts of projects. They don't say sort of when, where, or how projects should happen. There is some additional guidance provided in other international agreements. Two of the most relevant are the 1972 London Convention and the 1996 Protocol to that convention. Both of those instruments regulate dumping, which for the purposes of the convention is defined to mean the deliberate disposal of waste or other matter at sea. At the time the convention was adopted, the focus and the concern was really around discharges into the water column. And so there's some question as to whether the convention would also apply to the subsea bed injection of materials, as would occur in an offshore carbon storage project. That uncertainty has been resolved in the London Protocol, which expressly applies to the storage of waste or other matter in the seabed. The London Protocol expressly allows subsea bed storage of carbon dioxide for the purposes of sequestration, but under the terms of the London Protocol, those subsea bed CO2 storage projects require a permit from the country under whose authority or jurisdiction they occur. The United States isn't a party to the London Protocol. Canada is a party, but it hasn't fully implemented it domestically. So currently, Canada's domestic law doesn't allow the issuance of permits for subsea bed carbon storage. in both the United States and Canada, there's no sort of single comprehensive legal framework that applies to offshore carbon capture and storage. So in a project like Solid Carbon, where you have a number of different facilities being installed and a number of different activities taking place, a number of different laws and regulations could apply. In effect, each component of the solid carbon system would be regulated separately, and some parts might be subject to multiple sort of legal and regulatory frameworks. So this graphic shows the key permits and other approvals that would be required for different parts of the solid carbon system. And I just draw your attention to this reddish pink box up here, which shows the requirements for injecting carbon dioxide into the seabed. That requires likely a license from Natural Resources Canada and a permit from Environment and Climate Change Canada. Currently, neither of those government entities have authority to issue the required permits, but we do expect legislation to be introduced to change that. The legal framework in the United States is also highly complex. Again, each component of the project regulated separately. Some components of the project would require multiple permits and other approvals. And in some cases, there aren't established permitting processes, or they're quite complex. We are actively engaging with relevant government entities in both Canada and the United States to start addressing these issues, and we're quite optimistic that progress will be made. There is interest in both countries in advancing carbon removal and sequestration. Just last week at the COP, the US Secretary of Energy, Jennifer Granholm, announced that the Department of Energy would launch a new carbon negative Earthshot, which is intended to accelerate the deployment of carbon removal and storage technologies. And we're, as I said, optimistic that action will be taken to address some of these legal issues that could arise. So with that, I'll hand over to Terry to talk about the social acceptance piece.
Thanks, Romani. I can advance my slides. I may need help. Thanks, Romani, and thanks, everybody. My job is to make sense of how public groups are perceiving solid carbon at this early stage, and also consider some expert views as well. And I want to thank first Sarah Nawaz, who is at UBC in Oxford, and formerly Guillaume Peterson Saint-Laurent, who was a postdoc on this project as well. Both help I've relied on extensively. So it's difficult to predict what people will think, because if we look at prior responses to sort of large engineering projects to solve environmental problems, the response has been mixed. Often public opinion divides across starkly political or partisan lines. People are often resistant or risk averse at first, which makes sense. And this is particularly true for engineering projects that are seen as sort of not natural or messing with nature in some sense. But in the solid carbon case, next slide. In the solid carbon case, we're not actually seeing that right now. What we're seeing is about 57% of the public, that's the dark blue line. This is a sample of 2,000 residents living in a representative sample from Washington State and British Columbia, and 500 experts who are geophysical scientists or marine scientists working in the climate space. So about 57% of the public is supportive or strongly supportive, and about 52% of experts are. However, next click, we've got about 25%, give or take a few points, back to that last slide, please, who are ambivalent at this point, who neither oppose nor support solid carbon. So one of the problems here is that there's a lot of moving parts, as you've just learned, in the system. And when people are trying to make sense of new technologies, they don't necessarily look closely at the moving parts. They respond in reference to sort of positive or negative associations with different components. And so above sea level, you have these sort of positively valence components. You have wind energy, you have direct drawdown of atmospheric carbon. And below sea level, you have parts of the system that are more likely to make people nervous or to be negatively valent. So the vertical drilling, the spreading of CO2 into the basalt seafloor, and so on. So the question is, will the whole or the parts drive public thinking about this technology? So the positive above and the more negative below. And what we see is that, in essence, as concern about those subsea level parts goes up, support for solid carbon goes more or less directly down. On the other hand, you also see sensitivity to benefits. So as a benefit of solid carbon system, goes up. So these are benefits that include carbon mitigation and dealing with negative emission technologies that are needed, or even contributions to a green economy. As those benefits are perceived to go up, support for solid carbon also goes up. People are worried about other things, about the things mentioned already, the potential for monitoring leakage, whether or not they trust regulators to manage a solid carbon system. And also, interestingly, people who have a strong sense of responsibility for nature tend to be quite positive about solid carbon. Lastly, there's a lot of debate in the expert community about what they think will get us to 1.5 degrees warming by 2050. And 78% of the experts sampled here thought that removal of atmospheric carbon would be necessary. 72% thought that technologically engineered negative emission technologies were what were going to get us there. Was only 50% thought we could get there with control of human behavior, reduced consumption, and so on. And only 26% thought that natural-based processes would get us there. So big picture, there's more benefit appreciation than you often see at the early stages of this, no doubt because of sense of climate urgency. You also have experts who are on the same page about some big points. And you also have a fair bit of tolerance for these transformative technologies, which is often unusual. Thanks. I will turn the mouse over to Martin.
All right. Thanks so much, Romany and Terry. Thanks a lot for giving us these insights into the regulatory and societal considerations that will have a bearing on this kind of project. Now, let's take a look at the audience's answers to the questions from menti.com. So what did people think about our questions? Okay. Well, we see some agreement, which is great. I don't know how many people actually answered this, so I don't know how many people said no, but it's looking pretty positive. And so even if we stop all emissions, CO2 sequestrations will be needed in the future, seems to get a support. And even a bigger support, by a slight margin though, will be is for the project to be pursued any further. Do you want to comment on any of this, Terry or Romany?
I think it's similar to the results of the survey reported that people, there's a positive valence and toward this technology, complicated though it is.
So reflective of what we're seeing at the COP with the various announcements that countries are making to reduce their emissions, still not getting us to the goals of the Paris Agreement.
Yeah, that seems to be a common message there. And Terry, when you see this, we're doing this live here on YouTube and getting these questions, and I don't know, it's probably quite a much bigger effort for you to get sort of representative results from audiences.
Yeah, and we are dealing with people who are in the space of the pilot program and pilot rollout that we talked about. So the impact of that system would be more nearly felt.
Right. So maybe we need to do more of these live events to get quick answers, but also definitely rely on your expertise on interpreting these and doing a very thorough job. Okay, well, thank you both. Over to Tessa.
Yeah, thank you, all three of you, Martin, Romany, and Terry. So we're now reaching the end of the presentation part of our program before we'll head into the Q&A. But first, before we do that, I'd like to go back to Rachel for some insights into the outlook for this solid carbon project. What are some of the next steps for this project? What does the potential to upscale this technology look like?
Yeah, thank you. The next steps really are the solid carbon feasibility study or pilot study, which is planned for Cascadia Basin. And this study will combine 6 existing state-of-the-art technologies, but in a way that hasn't been done before. So on the left side is shown either a drill ship or a floating platform that would be used to inject the CO2 into the subsea floor using an existing borehole that was previously drilled for scientific research. The other technology involves a direct air capture that was previously discussed, the ocean floating platform that's powered by wind and thermal energy, CO2 injection into the subsea floor basalt, and then using the oil and gas drilling technology where it will react and become stable rock. Some of the risks can be monitored in terms of leakage and potential seismicity, can be monitored using the existing network in the Cascadia Basin that was completed by Oceans Network Canada. And we're in the process of developing tools to be able to, next slide, please. Sorry, mine's still not working. We're currently developing tools through research to understand the transport and mineralization of CO2, both during in situ injection and through time. So as was noted previously, we have our injection well. We have a dominant flow direction associated with groundwater movement in this permeable basalt aquifer. And we want to understand how quickly things are mineralizing and what sort of flow paths are developing as a result of those changes within the system. So we're also conducting reactive transport modeling to address the issue of scaling existing mineral carbonation technologies so that we can actually upscale this successful demonstration to actually tackle some of the problems that we've been discussing today. So I think I'm going to wrap it up there. So we do have time for questions. We hope you enjoyed this panel of speakers and agree that this ambitious approach in tackling new frontiers in chemistry and ocean engineering is worth pursuing. Thank you.
Oops, I was muted. Thank you so much, everyone in the panel. Great summary, Rachel, and Outlook, and also the other panelists. So we do have time for questions, and there have been some submitted in YouTube. And so, well, let's start at the top. There was a really interesting question about safety and the effects on the marine biology. So we didn't have a biologist here on the panel, but we can still discuss. So that was a question submitted by Kelly McDougall. Not sure if I missed this, but where is this shifting of the pH and temperature happening? Is this contained within the platform before injection, meaning not affecting the surrounding marine life?
I think I could take that question. So ultimately, the CO2 dissolving into the water in the aquifer is what's causing the pH change. And so where we expect that pH change is down 300 meters or so below the seafloor in this aquifer unit of the basalts. And so that's where all the CO2 is going to be injected, and that's where it's going to be impacting the pH of the water there. And again, the pH is not going to be that low. It's going to go down to, at the lowest about 4.5 or so. It's not going to be acid mine drainage levels of acidity.
That's great to know, Ben. Looks like organisms can remain there, and obviously it all returns back to normal, and anything that doesn't like that environment and moves out can come back later. There was also another safety question about triggering and triggering earthquakes, I think. And it is, the question was, it is my understanding that Cascadia is due for a massive shift. So while the stress regime may not indicate likelihood, can you comment on the predicted severity? And I guess I can take that because I'm looking at earthquakes in the area. And so right where this currently planned injection test will be, there's actually extremely little seismicity observed. We don't have anything right in the area, and there might be small tremors, too small for our instruments to locate them. But it is quite far away, tectonically speaking, for induced seismicity from the Cascadia subduction zone, where we do expect a mega shift at some point. We don't know whether it is in whether it is tomorrow or in a few hundred years, it's unpredictable, but it will happen one day. And from all the modeling we are able to do, there's absolutely no chance that we will ever affect that subduction big earthquake. So if we really pump hard and really push for it, we might be able to trigger a few small earthquakes offshore, which are unlikely to be felt onshore, but that chance it's both controlled by the injection rate as well as it is relatively low compared to what we know from the fault orientation. So seismically, there is little risk for offshore and no risk for the Cascadia subduction zone. But with our instruments on site, we will monitor what's going on, and should there be more than we expect, we can definitely control the injection rate.
Yeah, I think, Martin, just to follow up on that, I think one of the things that we know that's very interesting about this basaltic aquifer is how incredibly permeable it is, right? So even if we inject at quite a significant rate, it's going to be very difficult to induce seismicity. It's not as if we're injecting into these tight reservoirs that we see in places like Alberta, right, where the permeability is so low that the pressure can't dissipate and that you actually do cause fracturing or earthquakes to occur. And so I think that those factors combined all contribute to the, this extraordinarily low likelihood of earthquakes being generated. And as Martin says, even if they are, they're way out there at sea. So they're not going to impact anyone living on the island, for example.
All right. Thanks, Ben. One more follow-up question on the existing technology. So what is the greatest challenge to go offshore? So Ryan, Heather, or Karen, that's something for you. What's your experience? Where do you think your most challenges lie?
I can start us off here if we want. I think it depends on the technology, and it is basically a new industry. It's still in its infancy onshore, so taking this offshore is no small feat. So it does come down to performance, cost, and the fact that you do have to do it on sort of a microgrid. You need all this battery storage, etc. Looking more at kind of the specific technologies, if we look at the liquid side of things, it requires these huge contactors that they're susceptible to motion, and there's uncertainty there. They also require the huge amounts of heat that you need there. So currently with the liquid solvent side of things, it's 900 degrees Celsius met with natural gas. And so that would mean, shipping natural gas out to that site. And then if we look kind of on the solid side of things, there's a huge amount of uncertainty in the performance of the solid sorbents and how they perform offshore. No one's necessarily looked into it in great depth so far. And these solid sorbents, they take advantage of huge surface areas. 1 gram of sorbent has the surface area of the size of a football field. So you can see that these salt particles would have some sort of performance implications, which requires more research to be done on them.
For sure. Thanks, Ryan, for that. Anything to add from Heather or Karen? Okay.
Just to add, the whole offshore wind piece on the west coast of Canada and the US is nascent, but being developed particularly down in the US coast, and looking to do something on the west coast here in Canada as well. So that technology is coming and developing.
It takes time. I think that was one of the open questions for us all. And when it comes to in the summary of what we want to do next, there's the so-called demonstration or pilot or so. But thinking longer term, it's probably our multi-years, maybe decades, to implement something large scale that we envision right now. Because all these technologies exist, but there are definitely challenges, it looks like.
All right, I have a question. So I'm wondering, are there similar locations to Cascadia elsewhere in the world where this project could take place? Do you have examples of places where it could be similar to Cascadia? And why did you choose the Cascadia site initially in the first place?
I can speak briefly to that. Yes, there are globally many sites that would be ideal for this type of technology, but for the actual pilot study, it was ideal for us to locate ourselves somewhere that was, well, proximal to the US and Canada, turns out. and also in an area that has been really well studied for decades. So we have an excellent understanding of how fluids move within this system through a combination of geophysics and modeling and heat flow measurements that really give us an understanding of that system and the dynamics of that system. And as Ben said, relating it to earthquakes and pressure and all the other hazards, those have also been well mapped in this part of the world. And we know that this part of the crust is very permeable. So it is accepting of whatever is injected into it in a volume that can actually make a difference in terms of the demonstration phase. And yes, there are other places that have leveraged similar basalts, most notably in Iceland, where they were injecting directly into basalts at atmospheric conditions. And this is building on that success by, instead of operating in atmospheric conditions where you could have leakage directly into the atmosphere, we are putting in additional fail-safes through water depth and the sediment blanket that is essentially impermeable and keeping this trapped in the subsea floor.
Fantastic. Thank you so much, Rachel. I'm wondering if anyone else would like to comment on this, maybe Heather?
Yeah, so in addition, we have looked around the world to see where we think it might be most viable. And there's quite a few properties that we're looking for. So in addition to having permeable basalt, we want to have a thick cap rock for extra security, sometimes water depth for an additional fail-safe as well. And then we want to be in exclusive economic zones to try to make sure that the legality of what we're doing is clear. And what we found is that as you move away from the equator, because that's where you have more strong and steady wind, then there are lots of areas where we do have basalt, which seems like it is most likely viable, that meets all of the requirements and is actually close to wind that could power the system. So some of the countries that have a lot of capacity are the US and Canada. Iceland was mentioned, also Norway. There's some capacity in Russia and India, and to the south, Australia and New Zealand, and potentially Chile, Brazil, or South Africa are some major players.
Great to know. Thank you so much, Heather.
We do have some great questions coming in from the audience. So here's a question from Benjamin Tink. What do you expect will be the cost per ton of CO2 storage of the process at scale? Someone just moved that question out of my side. Okay. Would it be covered mostly through carbon markets or another co-product?
Somebody want to take that one? Maybe Curran?
Sure. So the point of the system study we're doing is to look at all these different options. We have an optimization framework to try and look at kind of trade-offs between different pieces. So, I mean, at this stage, our model predicts relatively high costs on the neighborhood of $800 a ton was our initial turn of the crank on the tool. But what we're looking for is both taking a look at cost progressions on direct air capture technologies as well as wind, et cetera. And then from a technical development perspective, looking at how we can integrate together the different pieces of our puzzle. So there's some thermal integration, there's some trying to bump up the capacity factor, how much of the wind energy can we use to run our process. So it's challenging, but we're trying to identify pathways that could work there. In terms of who's going to pay for this, the initial investors in this space have been companies like Stripe and Microsoft that are wanting to reduce their emissions. They're willing to pay quite a bit more than what you see in like a public carbon market or say the Canadian price on carbon currently. But that will develop over time. Carbon pricing is coming up, so it will kind of be anything you can do to reduce emissions will be remunerated at kind of that price, and at the same time, particular entities will be paying more. So we're kind of trying to drive down the cost of the technology, letting the markets develop for this and the regulatory structures. It's a challenging piece for sure. One of the reasons for using the offshore wind where we're looking is so that we're not directly competing with grid electricity or grid decarbonization using wind energy. So trying to do things that way. And then in terms of co-products and that's a bit of why we're including, say, hydrogen or ammonia production. So those are markets right now where you could sell green hydrogen, lots of talk of that at COP. So we're trying to look at, okay, if we had a revenue stream from that, how does that help offset the cost of the carbon capture we're also trying to do on these platforms and take a look at kind of business models like that as well. So hope that answers the question.
Thanks, Karen. Romani, do you want to
Yeah,
take?
I just wanted to add on the sort of who's going to pay for this and how do we pay for this piece. Karen mentioned the role of sort of carbon markets and offset markets, which we are seeing developing in a few places, and we expect to see sort of more development of going forward, particularly with the developments under the Paris Agreement, which expressly envisages the creation of this sort of international market, and the countries are working on the rules for that at the moment. I would also say that I think when we're thinking about sort of using carbon markets to pay for this sort of project has real advantages over some of the other carbon removal techniques that are commonly discussed, because the amount of carbon that you're capturing and injecting is relatively easy to measure and verify. Some of the other sort of negative emissions or carbon removal techniques, particularly the ocean-based techniques like ocean fertilization, ocean alkalinity enhancement, that measurement and verification is much, much more difficult, and that makes using carbon markets to pay for them much more difficult. So that is sort of one benefit of this sort of system.
And then the whole point of this is the carbonation part. So turning it in this mineralization. So at some point, it's rock. You don't even have to monitor it necessarily. So that's the push.
Totally agreed. Thanks, Karen. I think this solution is one of the most durable we can think of for the CO2 to be stored.
A related question, I guess, to the discussion that we're having now is whether this project could be used to deal with stranded assets from offshore drilling operations that we may see during the shift away from oil and gas industries towards more renewable sources of energy. So I wonder if anyone wanted to comment on that.
Yeah, certainly we've had conversations with quite a few companies kind of looking for, they're in that oil and gas space right now, but they're looking for how to transition. Lots of expertise there around the geology, around offshore operations, wells, etc. So definitely a lot of interest there. It's a little bit more regional, so North Sea, UK, oil and gas, shallow water is different than, say, trying to do kind of a virgin well on the west coast here into basalt, but certainly the industry behind that is wanting to kind of move in this direction, and lots that when we talk about the just transition idea, I think there is lots of opportunity for existing players in this space to transition over. We've looked a bit on the east coast of Canada as well for potential opportunities there. I was going to highlight to it with Heather's map. This is a global potential, so it's kind of nice. Kind of any country could pursue this, and as CO2 is a global waste product, anything you do anywhere in the world is beneficial globally. So I think there's some interesting opportunities there for kind of global partnerships, global deployments. And then with our system that we're looking at, we're trying to come up with a modular system that could be kind of mass produced. So it's scalable basically on a per unit basis that could then again be built locally around the world, deployed globally. That's the vision.
Mm-hmm. Yeah, thanks so much, Corinne. I love the piece about the just transition. We just have time for a couple more questions here, but we have another audience question that I'd like to highlight from D. Butterfield, Seattle, who asks, can you comment on the relative merits of land-based capture and pipeline to subsea bed disposal versus offshore capture?
Heather, did you look into this, or someone from your team?
Yeah, I can speak about this briefly. So the one of the benefits to onshore capture and sequestration is most likely cost, although we haven't finished costing out the whole system. And that's just because some of the technologies you need, like offshore platforms, ability to do maintenance, etc., do tend to add cost to your overall system. However, when you look offshore, you've got a lot of capacity. And again, it comes down to trying to move away from the grid and move away from that competition. So, and in addition, some of the costs that you would incur from offshore, you'll retain back because of things like the capacity factor. Like if you can go to areas that have very strong and very steady wind, sometimes you can get wind that's better than you could get onshore. And so there's sort of a trade-off of both systems, but overall, your ability to do something that's non-competing with the grid is definitely going to be better offshore in most cases.
Great, thank you, Heather. We have another audience question that's kind of connected to what you were just discussing from Alf Wilson. He asks, back to cost, what are the most expensive pieces of this technology? That is, where are the low-hanging fruit for decreasing cost per ton?
You want to take that one, Heather? You got the pie chart in your head.
Sure. So there's sort of three major cost components. The direct air capture itself is presently very expensive, but it's a relatively new technology, and there are a lot of people investing a lot of time and effort in getting that cost down as fast as they can. And they're sort of optimistic about their ability to do so. The second is offshore wind. Floating wind in particular is, again, a new technology, but again, there's lots of people working very hard to get those costs down. And the third one, which might be surprising, is actually the battery. Because we have to work offshore, the battery capacity to get sort of a balanced system is much more expensive than you might guess. And so that's why there's a lot of investment in sort of micro-controlling a grid and using fuel synthesis and battery storages of different types to really get a handle on that, because it can definitely drive up the cost of the system.
Oh,
Great.
Thanks so much. We have time for one more question, I think, before we need to wrap up, unfortunately. So the last question then is, what happens to offshore windmills when there are intense storms?
Hopefully nothing bad. So we design, I mean, you in principle could design a system to survive exceptionally extreme loads. So that's part of that global mapping we did, was to look at what are what we call met ocean conditions. So the combination of sea states, basically how big the waves are, with the wind conditions. And then you basically design accordingly, or you say it's too expensive to design for really extreme seas. We're not going to put them in certain places, but in others we can design to survive the load. So in really extreme conditions, essentially you would shut the turbine down, you feather the blades so they're kind of out of the wind, go into shutdown mode, and then you've got the floating platform would essentially ride out the seas. And you've designed, if it's a floating one, you have mooring lines with a certain amount of play in this system that can absorb some of those loads kind of dynamically. So it's manageable. You just have to design for it. And there will be a cost trade-off there again. So when we're looking at where to deploy, we could build, again, very heavy duty machines, deploy them absolutely anywhere. We're going to try and look for where are conditions kind of amenable to not having to kind of over design the turbines to again kind of drive down the cost.
Know what to expect. Thanks, Karen.
All right, so unfortunately, I think we have to wrap up the Q&A, but thanks so much to our audience for being so engaged and feeling excited about this project. We're almost at the end of our time for today's event. So on behalf of Ocean Networks Canada, the Pacific Institute for Climate Solutions, and the Virtual Blue Decade Initiative, I want to thank all of our amazing panelists for your presentations. Big thanks also go to Dwight Owens for organizing this event behind the scenes, and to Jennifer Putland and Ngaong Jamso for their technical support.
And of course, we also would like to thank our audience for joining this event. We heard there was some trouble with Eventbrite this morning, so sorry about that. But that was unfortunately out of our control. But we were very glad that you were able, for those of you who came, to be here. And we also really appreciate it if you can fill out our questionnaire for this event, so we can continue to improve for the future. So there's a link to a form, and that would be really great if you could take a few minutes, or just a couple of minutes to fill this out. Thanks.
Yep, and we'd just like to end on a final note by reminding all of us that 2021 marked the beginning of the UN Decade of Ocean Science for Sustainable Development. So we invite all of our participants to actively participate in this UN Decade, and especially in joining us to create an inspiring, engaging, and sustainable ocean. Thanks so much for joining us today.
Since 2006, Ocean Networks Canada's deep sea, coastal, and land-based ocean observatories have been bringing data to the surface for science, society, and industry. Our data informs discovery and decision-making. Everything from monitoring earthquakes and tsunamis to understanding whales, hydrothermal vents, and the impact of climate change on ocean systems and Arctic sea ice. With 15 years of continuous real-time open data, we now have a benchmark for monitoring our changing ocean. We've come a long way. In 2006, Ocean Networks Canada made history as the world's first large-scale interactive real-time portal into the ocean when a node was connected to the internet off the coast of Vancouver Island. This international collaboration marked the beginning of a new way of doing science, which enabled tremendous advances in the world's understanding of the ocean at a critical time. As we embark on the UN Decade of Ocean Science for Sustainable Development, it has never been more important to know the ocean. We are committed to world-leading innovation in ocean monitoring technology that will continue to grow Canada's leadership in ocean intelligence. As we look forward to the next decade of ocean observing, please join us to celebrate the successes, collaborations, and partnerships that made our first 15 years possible.